Okay, lesson 45. Using f, I think that says f prime actually, yeah. It's hard to see in there. It should say f prime. Using f prime to characterize f, using f prime to find maximums and minimums. So basically, a big part of calculus, or one of the things you often see is, they'll give you information about the derivative and they want you to kind of glean, okay, what the graph looks like based on what they tell you about the derivative, or maybe what they tell you about the second derivative, or, we're just working with first derivative today. So, as we look at A, we already know how to tell by a graph whether a function is increasing or decreasing. In other words, as we look at this graph that's sketched there, what is the graph doing, say, at point A? Is it increasing or decreasing?
Increasing.
It's increasing. Keep in mind, as we move from left to right, yes? So as my x values increase, as I move from left to right, my graph would be considered increasing here, right? What am I doing at B? At B, I am decreasing, because again, as I move left to right. What's at C? It's a min, right? So is it increasing or decreasing? It's neither. It's a minimum, right? And then at D, it is increasing. Okay, so that's just being able to visually look at the graph. The derivative can tell us all that information there, if we know the derivative of the graph. So now we can tell if a function is increasing or decreasing based on derivative of the function. If the first derivative is greater than 0, keep in mind greater than 0 in math terms means positive. So if the first derivative is positive for all x on that interval, then f is increasing on that interval. So they're talking about I being just an interval. So if the first derivative is positive at a point, the graph is increasing at that point. If the first derivative is less than 0, aka negative, then the actual function is decreasing. And then the other option, the derivative could be positive, negative, or the derivative could be 0. And if it equals 0, well, we already have talked. We set a derivative equal to 0, we are finding the critical points. Critical points usually, I won't say the word always, usually represent either a max or a min. Okay, on occasion we throw in something like an inflection point or something, but that's more related to second derivatives. Okay, so that's kind of the information to take in. Now, as we look at this one, shown is the graph of a function f. And one thing to watch for in calculus, especially like AP problems and stuff, pay attention to what graph they give you. Sometimes they'll give you f. Sometimes they'll give you f prime. Sometimes they'll give you f double prime. And so that's why I'm trying to make sure it's labeled. It'll always be labeled and always tell you. But this is f. This is the original function. From among the points labeled, choose those at which the derivative would be positive. So based on the fact that this graph is f, we want to know where f prime would be positive.
A and C.
Why A and C?
No. I was thinking it. Yes. I was thinking
You were thinking what?
I was thinking increasing, which means that the derivative is greater than 0. That's what the top said.
Right. So, and here's the deal, guys. Keep in mind, derivative is basically equivalent to what aspect of a graph? It's slope, right? We say slope of a tangent line. So it's the slope at that point. So if we're looking for where the derivative is positive, we're looking for where, I would think where the slope is positive. Officially, we should be looking for where f is increasing. But f is increasing is the same thing as saying where the slope is positive. Okay, so you could also think of it as slope being positive. So with that in mind, what are our solutions or answers? At point A, what is my graph doing? It is increasing, yes? So it has a positive slope around A. So A would be a positive first derivative. At B, my graph is decreasing. That'd be a negative first derivative, not what I'm being asked for. At C, increasing again, right? And so that's another positive slope. At D, it's decreasing. That's a negative slope. So negative first derivative. So answers of A and C. Are we okay with that? And you know, it is always a struggle getting it straightened out of which way we're going. Okay, it is. It takes a lot of thought to, figure out, okay, in this case, this is F. Okay, so the first derivative, think slope. Okay, officially increasing, but you guys probably think just as easily with slope. Okay, moving on. Example 2. If f is a function such that f prime is greater than 0 for all x, then describe the graph of f. Sketch how f could possibly look.
It would have to be some sort of diagonal line going down.
So essentially, what are you saying the graph has to do? If the graph is going from down to up, it is what? Positive. It is increasing. Okay? And so that's what we have to look at. Because it says such that f prime is greater than 0, that's saying such that f prime is positive, right? A positive first derivative, and we can think slope is positive. We can also think increasing, right? So if we describe it, we can say that f must be increasing because the slope is positive. And then we'll draw some optional pictures here, or some pictures that are options. So f must be increasing because slope is positive. Okay. So, what kind of things can we draw with a positive slope? Or increasing? The way Ross first described it, I kind of thought as a line. Because he said going from low to high, or I forget the words he used at this point, but, that was the descriptor there. And that's the key. As long as you draw a graph that's going from low to high, that's what we're looking for. Okay? So, a cubic is, increasing there. You could also have, I'm trying to think, how do I want to draw this? Okay. If you think about, let's see, this could be described as like an exponential curve. It's always increasing, right? Same thing about like a logarithmic curve. It's always increasing. Okay. We're talking about any graph that is always increasing. Okay. Questions there?
So could the cubic only be that as long as it doesn't have the max and min?
Correct. Yeah, as long as, it can't be the fancy cubic where there's the max and mins, because then you're throwing, it'd be mixed between, it'd go positive, negative, positive. So, yep. Okay. Example 3. Shown is the graph of some quadratic function f. So notice what it says right here. This is f. Okay, this is the graph of f. We're being asked to sketch the graph of f prime. So they're giving us f. We have to sketch f prime. And do notice what it says. It says that f is a quadratic, which that's something in my brain that is helpful. And in fact, I think I'll start with that. Okay. If it tells me that f is a quadratic, what power does that put in the problem? That tells me if f is a quadratic, there is an x squared in there, right? We're trying to sketch the graph of f prime. What are you thinking about f prime then?
So it would be power of 1, right? So you take the derivative of that, power of 1.
If you take the derivative of an x squared, you're going to get an x to the first. Or, I feel like I shouldn't have written the first on there because it kind of looks like a prime. Okay? But if you take the derivative of x squared, you're going to get an x, which represents what shape? A line, right? So when we draw f prime, we're going to be drawing a linear graph. Okay? Let's go analyze f over here. What kind of pieces can you tell me there?
So it's going to be right 1. So it would be x would be x minus 1 squared. And it's going up, I assume.
You guys are trying to write an equation for me, aren't you?
Yeah.
I don't want an equation. I don't want an equation. I get it. I'm not saying it's not doable, but it just so happens this one's a quadratic, and quadratics are easier to work with. Okay? That's not the direction that we're supposed to be taking. I'm not saying it wouldn't work, but what I want to look at, okay, so like, what would you call that point right there? A min? I agree, vertex. It's specifically a minimum here, right? And what do we know? That says minimum, I promise. Okay, what do we know about the derivative at a minimum? It's a critical point. So at this point, the derivative will equal 0. So when x equals 1, my derivative will equal 0. Does that make sense? So when I go over here to sketch my graph here in a little bit, when x equals 1, my derivative has to equal 0. So the y value will equal 0. Okay? What do you notice to the left of the minimum? What is my graph doing? We are decreasing over here, yes? Let's see, easier to write sideways on a paper. I don't know if I can do this on a board. This is harder than it looks. Probably looks awkward though too. Okay, so this side of the graph is decreasing, yes? Okay. When a graph is decreasing, what do you know about the derivative? It's negative. So what that says over here is that to the left of -1, it's going to be decreasing, so my derivative is negative. So that means my graph values are going to be, negative values are below the x-axis. Okay? So my derivative is negative there, has negative values, so it's going to be below the x-axis when we draw the f prime graph. And so guess what? What do you know to the right of that minimum? My graph is increasing. Well, this is a little easier to write. I don't know why, but if f is increasing, what do you know about the derivative? It is positive. So that means to the right of that x value of 1, my y values are positive in the f prime graph. Okay, I think we've got all the information that graph can tell us. So we're ready to draw a graph. In terms of x values, I'm putting the same x values that were on the original graph as my plan. That was f. Here I am drawing f prime. I'm labeling it f prime. Good habits here. Okay. Have you processed what we're drawing here?
It's going to start negative, come up to 1, get 0, 1, and just go up from there. So it would be like, would it not quite be like a cubic function type thing? Would it like almost do that? Okay, so it's just a line that goes through.
Okay, so if you recall here, and this way it worked in our, benefit. The original graph was a quadratic. So the derivative of a quadratic is a linear. So we know we're drawing a straight line. Because there is a critical point at x equals 1, a critical point is when the derivative equals 0. So the derivative equals 0 means there is a 0 on this graph. Okay, so what we're learning here is that zeros on the derivative graph represent mins and maxes on the actual graph. Okay? And then to the left of this, my graph was decreasing, which meant negative values. So that means I'm down below the x-axis. To the right of 1, I'm going to be above the x-axis. So basically, we're drawing a line that goes through the 0 of 1, an increasing line. Okay? We don't have a specific angle for this line. Okay? We don't know, that's not, we don't know enough to draw a specific angle of a line. But we know it's a line. Notice the left of 1 down here, my graph is in the negative y values. And that's because it was a negative value. It was negative slope over there. Over here, increasing positive slope, so positive y values above the x-axis. Kind of making sense? Oh, this is one of these things every year I have to review with myself. This is one of the things I have to sit and process to make sure I get it. I don't know. It's not one of those things that just instantaneously for me, always comes back. I have to sit and process. So I know you guys are going to have to sit and process some. Or maybe not. Maybe it's just me, but just saying. Okay, ready to try the next one? Example 4.
Is this a dang piecewise function?
Actually, no. They give us piecewise. The derivative is listed as piecewise, but we're actually going to draw just a normal graph. Okay? So, and that's the thing. We're not drawing this function right here. And even then, we're drawing f prime. Or we're drawing f. Okay, so assuming f prime exists for all values of x. So assuming nothing funky. That's the way I take that to mean. Sketch the basic shape of the graph of f given these following first derivative properties. So what I'm going to have us do is we're going to go through and analyze first. I'm not going to even begin to try drawing until we know what each and every little piece means here. So, f prime of x is less than 0 when x is less than 1. So less than 0 is a fancy mathematical way for saying negative. So when f prime is negative, so when the derivative is negative, what is my actual graph doing? Decreasing. So we know over here when we draw the graph, that f is decreasing. Okay, so when x is less than 1, our graph is decreasing. Okay. When f prime of x equals 0, what do we know when the derivative equals 0? It's a critical point, which means this is going to be a min or a max. Okay? And that is critical value, right? Critical point. Okay? Next one. When f prime of x is greater than 0, so greater than 0 is a fancy math way of saying positive. When my graph is, my derivative is positive, what is my original graph doing? It's going to be increasing. So when we draw our graph, it's going to be increasing from the x values from 1 to 2. When my derivative equals 0, when x equals 2. Derivative equals 0, it's a critical point, and so there's either a min or a max. And I think you got this next part figured out then, right? If my derivative again is less than 0, so if my derivative is negative, then at this point the graph is again, the original graph is decreasing. Okay. Now, I said min or max, min or max. Based on what we're told, can you identify which it is?
So since we're decreasing and then hitting min max, we're halfway in.
Yeah. So at x equals 1, you're decreasing to the left of it and increasing to the right of it. So if you're decreasing into something and increasing out of it, it's going to have to be a min. Does that make sense? Just, kind of draw it in your head, visualize. Oh, decreasing, increasing. Okay, that's a max, right? From when x equals 2, it's increasing before it, and then it's decreasing after it, so that's going to be a max. I didn't write that earlier, though, because I wanted you guys to, realize it's a min or a max, but we can tell which. We just have to think it through. Ooh, I don't like that line. Try again. That's a little better. Let's see, what x values do I need? I really only need x values 1 and 2, don't I? Okay. Now, what we don't really know here what we don't know is we don't know anything about y values. I just leave it at, yeah, I'm not labeling the y-axis because we don't know where this graph really is, okay? We just don't know that. And we don't know, unless I'm overlooking something, we don't even know and have enough information to know if there are zeros, okay? So we don't know. Usually when I draw this, like if I look at my notes right here, I have my graph all above the x-axis. It's one of those things that doesn't really matter where it's positioned. It matters the shape of the graph. because that's what we're trying to do. It's all about the shape. So, okay, to the left of 1, what is my graph doing? It's decreasing. So we're going to be going down, right? At 1, we're going to hit a minimum. From 1 to 2, my graph is increasing. At 1 or at 2, I'm going to hit a max, and then afterwards my graph is decreasing. Okay. A graph that has a shape that has a minimum at x equals 1 and a maximum at x equals 2. This isn't the only option for the graph, right? But this is the basic gist of it. Questions there? Okay. Moving along. This might not be a good one for me to have at the bottom of the screen, but that's all right. Assume the graph of f prime is the graph below. Determine the basic shape of the graph of f. So kind of the same thing as last time. They're giving us f prime information, right? We're trying to get the basic shape of f. Let's see.
So is it doing backwards this time?
What?
So we're doing it backwards this time?
From the previous page?
Right.
Yes. In my brain, I was thinking, okay, the same as the example above it, in that they're giving us the information of f prime. They're giving us the information of f prime. We're trying to get to f. Okay, but if you're comparing to the front page, it is backwards, isn't it? Yeah, because there they gave us f, and we had to come up with f prime. Again, there's a lot here to take in. I know. At least in my brain there is. My brain struggles taking this all in. So, okay, what information can you tell me from that graph? Okay. So we have zeros. I'm just writing some information. So the derivative equals 0 at x equals -2 and 4. So if the derivative equals 0 there, those are going to interpret into mins or maxes, right? At -2 and 4. Obviously going to be one of each. We just haven't gotten far enough to know which is which. What else? Where is my graph? Where is my derivative between -2 and 4? Where is this graph? It is negative, yes? From -2?
Which means decreasing between those two.
Right. From -2 to 4, my derivative is negative, which is going to result in a decreasing graph. So I'm going to say that f prime is less than 0, aka negative. So that means we're going to be decreasing, and that's going to be from -2 less than x less than 4 if you want the official math notation. So my graph's going to be decreasing between those -2 and 4. What's that mean to the left of -2 and to the right of 4? Yeah. My graph is positive here and positive here. It's positive because it's above the x-axis, right? Positive y values is what I mean there. And so then, when my derivative is greater than 0 or positive, those are going to mean increasing pieces of the graph. So my graph is going to be increasing when x is less than -2 and when x is greater than 4. you officially have all the information you need. The one other small piece of information, if you wanted to, and it won't always work here, but what does the shape of the derivative look like? A quadratic. So if, running out of room here, if the derivative is a quadratic, what could you glean?
It's cubic.
That we're going to be drawing some kind of cubic, right? Keeping in mind, this cubic is going to have a min and max in there. Sorry. My phone is not silenced today because of stuff.
So that should be my day.
Huh?
That should be my day. A little mini.
Well, depending on the notification, it's either a minion or it's a Groot. So, just depends. Okay. We ready to sketch this guy? Obviously, I need to label over to 4 and over to -2, right? And we are sketching F. So I'm trying to be good about labeling that we are sketching F. Okay. And again, we don't have the information necessarily to know or to worry about zeros. Okay. So, what are you going with here?
So we're going to start increasing.
Yeah. When x is less than -2, we're increasing. We had a positive derivative, so we're going to be increasing. We're going to increase to a max. We said at -2 and 4, we're a min and a max. We just didn't clarify which. Obviously, if I just increase to the left of it, I'm going to a max. And then after I increase from -2, now I'm going to have to decrease to 4. And again, I'm just drawing a graph here, okay? I'm decreasing to 4. At 4 is obviously going to have to be a min, because it was either a min or a max. And then after 4, I am increasing. It's a cubic, yes. Kind of a stretched out one the way I drew the graph, but it's a cubic. Okay, take the time to just dissect these pieces. You will definitely see stuff like in AP, like multiple choice questions and stuff, where whether they give you a chart of information, whether they give you a graph, you know, they want you to be able to answer questions about it. So, okay, ready for the bottom half? Gotta keep us moving here, I guess. Using f prime to find maxes and mins. Kind of already been doing this, but going right along with it. Suppose f is a function such that f prime of 1 equals 0. F prime is positive on the interval -3 to 1, and f prime is negative on the interval from 1 to 4. Sketch the graph of f for values of x near x equals 1, and indicate any special characteristics of f. Okay. So, notice we're talking about f, right? Notice that we're going to be sketching the graph of f. Okay. But all this information they're giving us is about f prime. So let's go through and analyze the information they give us about f prime. A function such that f prime of 1 equals 0. What do we know? It's a critical point. It's a critical point, and so that means there's either going to be a min or max. We can come back and figure out min or max here before long after we know what it's doing to the left and right of 1. F prime is positive on the interval from -3 to 1. If the derivative is positive, what is the graph doing? Increasing. And f prime is negative on the interval 1 to 4. If the derivative is negative, what is the graph doing? Decreasing. Don't know I can write this one in here very well, can I? Okay. Sketch the graph of f for values of x near x equals 1. And indicate any special characteristics. Let's see. We know we're talking about x equals 1. Okay. Well, what are you seeing? Have you figured out what's happening at 1? A max, yes. We're going to end up with a max because from -3 to 1, we know the graph is at least increasing. At 1, it starts decreasing. We really don't know the graph of it past there. But we know enough to kind of sketch basically a parabola, it looks like, right? We don't know information past there, so who knows what it does. Irrelevant to this problem. So we sketch the graph for values near x equals 1. Any special characteristics? We already talked about it. What special characteristics did we determine on this graph? The fact that there is a max. That's the special characteristics we're looking for. Okay, so there they gave us the information. They said sketch a graph. Actually, did they actually? Yeah, they said sketch the graph, but the special characteristics, we came up with a max. One more. Use the first derivative to demonstrate that the function f of x equals x squared plus 2x plus 3 attains a relative minimum at x equals -1. Okay, so this is more of a prove it. They're telling us, hey, there's a minimum. Okay, they're telling us there's a minimum. We're going to use the first derivative to prove that.
Are we just going to get the first derivative and graph it, or are we going to get the first derivative and like plug in values?
More of the plug-in values. Okay. Is it all? Nope.
All right.
Oh.
Maybe not. Never mind.
Okay.
Thank you.
You said this was Paulus, right?
Yeah, it says on the bottom.
Yeah, that's what I thought. Oh, go for it. Okay, so this is more to demonstrate, this is more of a prove it. So use the math to prove it. Okay, so first of all, it says to use the first derivative. So we should probably find first derivative. What is the derivative of x squared plus 2x plus 3? 2x plus 2, yes? Okay, so what is one piece of information that would prove there's a minimum at -1?
If before -1 it was decreasing and after it was increasing.
Okay, and I wasn't even going to get to there. I was going to save that for a second, but yes, so before a minimum, the graph needs to be decreasing. After the minimum, the graph needs to be increasing. What needs to happen at the minimum in terms of the first derivative? E equals 0. So to demonstrate, one thing we're going to do is I'm going to plug in -1 here. If you plug in -1, 2 times negative 1 plus 2. Well, guess what? Right there, the derivative equals 0. Derivative equals 0, I've been saying it all day, means there is a min or a max. So right there, we've demonstrated that there's a min or a max happening. That right there is not enough, because you've just demonstrated it's a min or a max. We need to show that it is specifically a min. And so leading up to a min, we need to show that it is decreasing, right? Because you decrease down to a min. How could we show that this derivative would be decreasing before there?
Plug in a value before that.
Okay.
Plug in negative 2.
Plug in a value less than negative 1. Okay? I would pick a value close to negative 1. You don't want to go too far away, because if you go too far away, maybe you're going to be past another there's other stuff happening possibly. But, so we're going to plug in negative 2 is a good one. So if we do 2 times negative 2 plus 2, then we find that that is negative 2. A negative first derivative, right? So right here, we just showed that the first derivative is negative at that point, and a negative first derivative says that the actual function then is decreasing. Right? So if the derivative is negative, the graph decreases. I guess I should write that out a little bit better. Okay? Again, you can't stop, because if it's decreasing on the right of it, then it's just an inflection point. It's not actually a min. So now we have to pick a point to the right of negative 1. I'm just going to pick 0. I like using 0 anyway. 2 times 0 plus 2. So my derivative at 0 is 2. So that means my derivative is positive, and a positive derivative indicates that the graph is increasing at that point. So it increases. So decreasing, a critical point, and increasing is going to show that yes, it is a min. Okay? So they use the word demonstrate. We're proving it. We're showing it. But those are the pieces you have to consider. Okay? If on a, what do I want to call it? Not a multiple choice, free response. FRQ, there we go. If on a free response, you have to somehow show that, state that it's a min or a max, there's your proof. Okay? And I got done with time to spare.
Monday is word problems.